Hey y'all. So I decided to do a module 2 video, right? Just going over module 2 and its components, I guess. I wanted to do this video because I wanted to go over module 2 as quickly as possible with y'all. So next workshop, when I see you all, we can go into module 3, which I believe you all will need a lot of help on as well. But at least I'll be there to answer your questions, right? And next time I see you, if you have any questions regarding this video, you can go ahead and ask them. But right now, I want to introduce you to the material. So then you can do practice problems and then go into workshop more prepared, right? So, I mean, the point of this video is for you to see the material and then be like, oh, okay, this is what I have to do. And if you get stuck in a homework question, I guess you could, ask for help and kind of already know what we're talking about in workshop. Okay. So module 2 basically just talks about Lewis structures. Lewis structures are a way for us to visualize the compound, a compound. I have 4 steps to find the Lewis structure. I promise I'll make it easy for you all. But yeah, let's go ahead and get into it. So say I wanted to find the Lewis structure for carbon dioxide, right? CO2. CO2. We have 1 carbon and we have 2 oxygens. The first step to finding a Lewis structure is to count your total valence electrons. Right? That's the valence electrons for carbon and the valence electrons for oxygen. Okay, the way we find valence electrons are through the periodic table, right? So from hydrogen to beryllium, and then we skip the transition metals and we go on to boron all the way to helium. Okay, so counting from hydrogen, we have 1. Sorry, I covered up. We have 1, 2, boron is 3, carbon is 4, nitrogen is 5, oxygen 6, fluorine is 7, and then helium is 8. Now it's not just those elements, it's the whole group, right? The whole group of oxygen has 6, the whole group of boron has 3. Yes. So that's how we find the valence electrons. Okay. That's our first step. Our second step will be dumping the valence electrons into a rough sketch of the Lewis structure. So we put all of the valence electrons into a rough structure, and then from there, what we do is find any members that follow the octet rule. Yes. So what I mean by this is after you have all the electrons in your rough structure, you want to check to see if you have any elements that have to follow the octet rule. Now the octet rule basically, it's 4 elements that have to have 8 electrons around them. They just have to, right? And you have to follow this for every Lewis structure, because if these 4 elements don't have 8 electrons around them, they become unstable and it's just the wrong structure. Okay, so third step is check for octet rule, check for octet. And the 4 elements are carbon, nitrogen, oxygen, and fluorine. I like to remember it by CNOF. CNOF. Okay. And our final step after finding, after rearranging the electrons to make sure that these 4 elements follow the octet rule, the final step is formal charge. The way we find formal charge, the way that I like to remember it is once minus has. By once, I mean how many valence electrons does an oxygen atom? How many valence electrons does an oxygen atom want? Minus how many valence electrons the oxygen atom has around it in the current structure. Right now it's a little confusing, right? But if we go into just some problems, you'll kind of see that'll follow this structure. So let's go ahead and get into drawing the Lewis structure for carbon dioxide. Okay, so our first step was counting the total valence electrons. So we have one carbon, we have two oxygens, right? Carbon, via the periodic table, wants 4 valence electrons. 4 valence electrons, yes. And then oxygen wants 6. But we have 2 oxygens, so we have to multiply that by 2. Yes? So we have 4 valence electrons for carbon, 12 for oxygen. All we have to do now is just add them up, right? We get 16. Our second step is to dump all of these electrons into a rough structure, okay? The way we find a rough structure is just to put the odd atom, which is carbon in this case, in the middle, and then have it surrounded by oxygens. So carbon is going to go in the middle because it's the odd one out. Yes? And then we have 2 oxygens around it. Okay, cool. So it looks wonky, but this is a carbon, this is an oxygen, oxygen. This is a rough structure, right? And we know that an interaction has to happen between carbon and oxygen. By interaction, I mean bonds. We know that there's going to be at least a single bond between oxygen and carbon. We don't know right now if there's going to be a double bond or a triple bond, but as of right now, we know that there's going to be a single bond, at least. Okay? Okay. So we have to dump all of these 16 valence electrons into this structure. Okay. So the way we dump them in is we start from the outside atoms, in this case oxygen, into the central atoms, in this case carbon. So the way I like to do it is dashes, right? Each dash is going to represent 2 electrons, right? Just like this bond represents 2 electrons. Okay, so each dash is going to be 2 electrons. So I'll just divide this number by 2, and we just need 8 dashes. Again, each dash representing 2 electrons. Cool. So let's go ahead and dump them in. Remember, outside first, inside last. So we already have some electrons here, so we'll count them in our total count. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's all of our electrons. Okay, we counted these single bonds into our total count, and we just filled in the oxygens, right? Remember, an atom can hold up to 8. Okay, there are expanded octets and there are incomplete octets, but right now, just know you have to fill in 8. Okay, 8 electrons per atom. So that's our second step, right? We already put all the valence electrons in. Our third step is to check for any atoms that need to follow the octet rule. Now, remember, those atoms are CNOF or Func, if you would like to remember it that way. So oxygen, we have oxygen here, but we also have carbon. Now let's check if carbon and oxygen are following the octet rule. Okay, so then we have 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is following the octet rule. Okay, and this one looks the same, so it must be true. Okay, now for carbon. Carbon, we just have 1, 2, 3, 4. We just have 4 electrons around it. Now we need to fix that. We need to have 8 electrons around carbon because carbon has to follow the octet rule. The way we do that is just to take 2 electrons from oxygen and have oxygen share electrons with carbon. A double bond. Okay? Okay, so let's check if oxygen still has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. It does, right? And we just added 2 more to the count for carbon. Okay, but we need 2 more, right? That's 6, we need 8. So we're gonna do the same thing with this oxygen. Our last step is to check for formal charge, okay? Everybody's happy, everybody is following the octa rule, everybody who has to follow the octa rule is following it. Okay, so then now let's check for formal charge. Formal charge, remember, is just want, which is the valence electrons in the periodic table, minus has, which is the valence electrons that are found in your structure. Okay? The way we find the electrons in the structure is we cut these bonds in half. Okay? So instead of them counting as 2, they count as 1 electron, because we just want to see the electrons around oxygen for formal charge. Okay, so only for formal charge we cut these in half. Okay? Okay. So let's check oxygen. Oxygen, we know that it wants 6 valence electrons via the periodic table. So it's 6 minus, so now let's count how many electrons it has, right? It has 1, 2, 3, 4, 5, 6. Remember that these count as 1 now because we cut them up. 0, right? That's fine. Okay. Now this oxygen looks the same, so the charge must be the same. Now let's check carbon. So carbon wants 4 from the periodic table, and it has 1, 2, 3, 4. 4 around it, which is 0. So it's 4 from the periodic table and then around our carbon atom. So it's 0. This is actually the best structure you could have, because one thing about Lewis structure is that the best structures have a central atom charge of 0 or close to 0. Yes, you want to strive to get this central atom as close to 0 as you can. Well, this actually checks out, right? There are no charges in any of these atoms. That makes sense because carbon dioxide is a neutral compound. Let me actually make a note about what I said about the central atom. Formal charge of 0. Okay, if you can get your central atom charge to 0, then go ahead and do it, right? Because you want the charges to be in the outside atoms rather than the central atom. Okay, cool. So that was the Lewis structure for carbon dioxide. Now let's go into nitrate via the rule of 7. We know that is NO3 minus. Now let's go ahead and count the total valence electrons. Nitrogen, we have 1, we have 3 oxygens. Nitrogen wants 5, and oxygen wants 6, but we have 3 of them, so we have to multiply by 3, which gives us 18. Okay, 18 plus 5 is 23. Okay. So this doesn't really make any sense, right? Because you have lone pairs, not just, electrons just floating around by themselves, right? Does that kind of make sense? The electrons go in pairs. So to have an odd number is kind of like a red flag whenever you're drawing a Lewis structure. But what we have to take into account as well is the charge of our compound. In this case, nitrate has a charge of -1. Now, the way that you include the charge is kind of unintuitive, right? You see a -1 and you're thinking, okay, just subtract 1, but that's not the case. You have to add 1, right? The reason is because we're counting electrons, and electrons are negatively charged, okay? In reality, I guess we could make this number negative, right? Because we're counting negative charges. So to include the charge, if we have a negative charge, we have to include it into the count. So it's negative 23 minus 1, which is just 24. Negative 24. But it's not really negative, right? I just made it negative. So you can kind of see how we include charges. If it has a positive charge, then you subtract, right? Because electrons are negatively charged. Yes? Okay. So in reality, we have 24 valence electrons, including our charge. Okay. And by the end of this structure, we should have a -1 charge in total. Okay. Step 2 is to dump in valence electrons into a rough structure. The odd one out here is nitrogen, and you're going to have 3 oxygens around it. Now, we don't know if we're going to have a double bond, triple bond, but we know that for sure at least one interaction is going to happen between nitrogen and these oxygens. So we're just going to go ahead and draw one single bond between them. Okay. Now we have to dump in our valence electrons, right? We start from the outside atoms into the central atom. Okay, so we need 24 valence electrons, which means we need 12 dashes. Remember, each dash is 2 electrons. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we have our 12 dashes in. Now our next step is to check for CNOF, right, for the octet rule. We have oxygens, and we also have a nitrogen. These oxygens, as we saw last time, are following the octet rule, right, because they look similar. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around them. They're fine. The one that's not fine is nitrogen. Nitrogen has 6 electrons around it, but it wants 8. It has to have 8. So we're just going to borrow 2 of these electrons from oxygen, and we're going to put them over here with nitrogen. Yes. Okay. Now nitrogen has 4 dashes, meaning 8 electrons around it, so it's fulfilled. So octet rule is fine. We're good. Our final check is for formal charge. Well, basically it's 1s minus 1, 2, 3, 4, 5, 6, 7. But an oxygen with 3 lone pairs and 1 bond has a charge of -1. Yes, that's because it wants 6 from the periodic table, and it has 7 electrons around it, so it's a -1 charge. Okay, that's fine. Now this one is from the last example. It has a formal charge of 0. Okay, now let's check nitrogen. So we have 1, 2, 3, 4. Nitrogen wants 5 valence electrons from the periodic table, but it has 4. So we have a +1 formal charge. Remember this note? Well, you don't have to remember it, it's written right here. This note says that the best structure has to have a central atom charge of 0, or close to 0. In this case, we can't make nitrogen 0 because it has to follow the octet rule. If we take electrons away, it won't follow the octet rule, and if we add more electrons, well, it's going to be an expanded octet, and it still won't work. Okay, so unfortunately, we can't do anything about it. We have to have a central atom formal charge of 1 because the octet rule has priority over formal charge. Okay, cool. So this is our best structure. Now, before I erase the structure, I want to go over something called resonance. So in the real world, we have this nitrate structure, right? But it doesn't necessarily have to look like this, right? It could have a double bond anywhere else, really. It doesn't have to have it on the leftmost oxygen, or it doesn't have to have it on the, I guess, upmost oxygen or the rightmost oxygen. In reality, this double bond can go into any oxygen, and it would still be the same structure. So a resonance structure is basically just the same structure, but differing on a double bond. Yes, the double bond just differs on the position where it's at. And how we kind of show that with drawings is we put this in brackets. Oh, I kind of ran out of space, but this is a bracket. We put the charge out here, and then we draw these double arrows, signifying that they're the same thing. They could go, the double bond could be here, or the double bond could be here, or whatever. So we put this double arrow, we draw these brackets, we put the charge, and then we draw the same structure. You could draw the resonance structure with the double bonds in different positions to signify that, okay, it could exist, it could look like this, but it could also look like this, and it could also look like this. First step, find the total valence electrons. Second step, dump the electrons into a rough structure. Third step, check for octet rule. Fourth step, formal charge. Yes, formal charge is ones minus halves. The octet rule members are CNOF. Okay, so the next thing we're going to talk about is hybridization. Okay, so hybridization is it's pretty easy to find. I'll just go over one example, and then after that we'll just move on to geometry. Okay, which should be the last thing that is on module 2. So let's just go over hybridization first, and after that let's go over geometry. So first of all, let's do our steps. So let's count up total valence electrons. Okay, so again, it's an odd number, but we have to take into account the charge, right? Okay, so we have a charge of -3. So since it's negative, again, these electrons are not negative. This count is not negative, but because electrons are negatively charged, we add negative charges instead of subtract them. Okay, so we add 3. So we should get 32 valence electrons. Okay, 32 valence electrons total. All right, so I wrote this too big, but okay, let's draw our rough structure and dump in these electrons. So phosphorus should be in the middle, surrounded by 4 oxygens. Okay, we know that at least one interaction is going to happen between them, so let's just draw a single bond. We don't know if there's going to be 2, 3 bonds. We don't know. Okay, cool. So we have 32 valence electrons, or we have 16 dashes, right? Because 16 times 2 is 32. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, remember, outside in, we're cool. So we already dumped our electrons. Our next step is going to have to be CNOF, right? We have to check for the octet rule. We have oxygens, which they all follow the octet rule right now. And we have phosphorus. Phosphorus does not have to follow the octet rule, so it's fine. Even though it has 8, it's fine. Step is to find formal charge. So from the nitrate example, we know that all of these have a -1 charge. That's fine as long as we can reach a formal charge of 0 in our central atom, right? From the periodic table, we know that phosphorus wants 5, and it has 4 around it, so remember we cut these in half and count them as 1 instead of 2. Here we can get a 0 formal charge in the central atom. We can, because well, we can borrow one of these, two of these electrons from oxygen, right? Now oxygen has a formal charge of 0, and phosphorus, yes, okay. So now all of these charges have to add up to -3, and they do, right? We have 0 here, and we have a 0 here, and then we have -1, -1, -1, 3 times -3. Okay, cool. So this is our best possible structure. A double bond, 3 single bonds, and a phosphorus in the middle. We could have a question where it asks us to find the hybridization around the phosphorus atom. The way we find hybridization is we use the electron configuration notation, right? Remember, you have the S block, you have the P block, you have the D block, F block. So we use that same notation. So all we want to do is just count electron regions, right? And it can get a little confusing, right? Because bonds count as electron regions, and lone pairs count as electron regions. Okay. So we're asked what's the hybridization around the phosphorus atom. So we count the electron regions. So we have a bond here, that's one region. We have another bond here, that's another region. We have another bond here, that's another region. Now we have this double bond, right? So no matter if we have a double bond or triple bond, it's still going to count as one electron region. Find its hybridization. We just do the following. It's just, we start from S, and then we keep adding on P's and then D's. Okay, I know it sounds weird, but it's basically S for one region, SP for another region, SP2, SP3. That's it. Okay, so the hybridization around the phosphorus atom is SP3. It's SP3 hybridized around the phosphorus atom. Yes, so you count from S, and then you go add P's. Yes, and the reason we do this is because we're sort of filling in electron boxes. If you recall from Chem 1, remember that the S block has one box, right? So we're filling in that box. The P block has 3 boxes. So we're filling in those 3 boxes. And then the D block has 10 boxes. So after you fill in the P orbitals, then you go on to the D. That's the reason that we count like that, right? Because it's this region fills up the S block. This region fills up, okay, so it fills up the S block. This region fills up, the second region fills up this one fills up this one, and this region fills up this one. So that's why we do S, SP, SP2, SP3, hybridized. But that's just for the phosphorus atom. Cool. Now let's do oxygen. Say the question asks, okay, what's the hybridization of the double bonded oxygen atom in a phosphate Lewis structure? So let's just count up the electron regions. Remember, lone pairs count and bonds count, obviously, because they're all electrons. So for this oxygen atom, it'll be this region right here, this other region right here, and then it'll be these double bonds. But the double bond counts it as one region, just one. Okay. So we have 3 regions, so it's S, SP, SP2. So this oxygen atom is hybridized as SP2. That's how you find the hybridization. It's not too hard, but you will get the wrong hybridization if you get the wrong structure. Okay, so just go ahead and practice it. So let's go ahead and talk about geometry, right? So hybridization, we already talked about Lewis structures. One final thing in this module is basically just geometry, right? So what we've been doing is drawing Lewis structures in a 2D world, right? It's flat, up and down, side to side. It's fine. But I mean, we live in a 3D world, so in order to accurately represent these Lewis structures, we have to take into account geometry. Actually, before I start with an example, let me just kind of go over how I see these geometries, and maybe it'll make sense for you. On the back of your workbook, behind the periodic table, you have this chart that tells you the hybridization and the electronic geometry and the molecular geometry, right? So electronic geometry is just taking into account the electron regions, right? But molecular geometry takes into account the lone pairs and the bonds. So how I see it is I'm just gonna use circles. They don't really represent elements. It's just circles right now. So if we have this, if we have something like this, then its electronic geometry would be linear, right? I mean, it's just a single bond. We could have a double bond as well if we'd want to. If we'd really want to, we could have a triple bond, but its geometry is going to be linear. Pretty straightforward, right? You have three atoms connected to a central atom, trigonal, and then it's planar. So I guess I like to think it's flat. We'll see right now variations and how the names differ, but right now we're just going over the electronic geometries. So this is trigonal planar. If we have something like this, its name is gonna be tetrahedral. Okay. Now, so you kind of see a pattern, right? We're just adding atoms to a central atom. So here we have one, we have three, atoms around the central atom. We have four, and then we could have five, right? Which kind of looks like a tetrahedral, but it kind of in the 3D world, you have this one kind of sticking out. I know it looks close to this one, but it's sticking out. I'm not the best at drawing. But five atoms around the central atom is trigonal bipyramidal. Now, you can kind of see where they get the name from, right? Trigonal from these three atoms surrounding the central atom, and then bipyramidal because if you connect these, I'm not the best at drawing, but if you connect these in a 3D space, you get two pyramids on the top and the bottom. Yes? And then the last one that we're going to cover, at least in Chem 2, is octahedral. It has 6 atoms around the central atom, right? And this is called an octahedral. Octahedral. Yes, it's kind of like a step up from the tetrahedral. Where the name varies is if we take away elements and sorry, not elements, but if we take away atoms, right, we start getting different names and different structures, right? For linear, we just have linear. You can't, like I said, you can't really take away an element, an atom, and just replace it, and then you won't really have a geometry, right? Linear is always going to be linear. Electronic and molecularly. Trigonal planar, however, you can take away an atom, right? It doesn't necessarily have to be the top one, but due to VSEPR theory, right, the electrons are going to repel in such a way that they want to be as far away from each other as possible. So, no matter which atom you take away, trigonal planar, if you take one away, it would kind of take this this shape, because these two want to be as far away from each other and as far away from the lone pair electrons, which is these two. Okay, now we do have different names for, if you start taking away atoms, we do have different names for all of them. But if we take away an atom from a trigonal planar, that's going to go into a bent geometry. Yes, a bent shape, because these two are repelling from the lone pair electrons as well as they're repelling from themselves. Okay, and if you take another one away, well, you're just going to be left with a linear. Okay. So then for a tetrahedral, if we were to take one away, say we took one away, it would take away this kind of shape, right? I mean, it went from like this. It went from this because these are trying to constantly repel each other. So this distance is the least amount of energy for the electrons, right? They're all kind of equally away from each other. But now that we took one away and we added lone pair electrons, they're trying to get away from the lone pair electrons as well as themselves, right? So it would take this kind of shape. And as you can see, it kind of looks like a trigonal. But we have these electrons, so it kind of takes the shape of a pyramid. And that's the name. It's trigonal pyramidal. Trigonal pyramidal, not to be confused with trigonal bipyramidal, which is the electronic configuration of 5 atoms around the central atom. Trigonal pyramidal. And you would keep going like this, right? If we were to take another one of these atoms away from this shape, we would end up with something like this, where you get kind of like bunny ears. You get kind of like bunny ears. Okay, so now it looks very similar to the bent shape. So that's its name. It's a bent. Now you might be thinking, okay, well, I mean, I just have to learn this for this module and then I'm good, right? But this is going to come back in future modules when we talk about polarization. So geometry is important because not only does it accurately represent a structure in a 3D world, but it also helps us understand its polarization and if it's polar or non-polar, which then can help us understand how this compound behaves. So this is really important to chemistry. We have to understand, okay, what's the structure? How does it affect the compound? So that's why geometry is important. So with that being said, the names get kind of wonky as you keep going along. If you keep taking away atoms from like an octahedral, you get names like seesaw, you get T-shape, whatever, but they're all really trying to represent kind of accurately how a structure would look like in a 3D world. And well, that's the point of geometry. So with that being said, I'll end the video on this note. Okay, so please just go ahead and do your practice problems and your homework, and I'll see you all next week.